Hello, today I want to introduce this paper, VAEBM, a symbiosis between VAE and energy-based model. This paper is published in ICR 2021 as a spotlight paper. This paper is from a PhD student from University of Chicago during the internship at NVIDIA. The author has published his presentation video online. Yeah, just in 9 minutes, I think. Yeah, not I think it's 9 minutes. Okay, first give a short summary. We know the VE and the energy-based model are both generative model. Uh, of course, they have their potential problem. From the mathematical definition or the objective function, VE defines the elbow of the log likelihood, and energy-based model has its own uh, likelihood definition. So the authors of this paper combine these two models to reduce to reduce the problem from of both both models. But to optimize two models is not very it's not easy. So the authors they use a two-stage training method. First, they train a VE. They train the VE independently. They use a NVE, the state of our VE, and then second stage they fix the VE and they use the reparameterization trick to sample the negative samples from the joint space of epsilon z and epsilon x, to get the to for the energy-based models updating. Or we say the energy-based model uh, is to refine the data refine the distribution, refine on this one. The final performance of this model is very good. But I think potential problem is they have a huge parameter, a huge set of a huge set of parameters, because they use NVE. It have a lot of parameters. Let's talk a bit about the background. First is the energy-based model. It defines the likelihood of X as a Gibbs distribution, it's also named Boltzmann distribution with with energy function E theta of X. This energy function returns a single value, a scalar, and the denominator z theta is the partition function. It's the integration over all x, so it's intractable for much for the maximum likelihood learning. The gradient of this likelihood can be computed by this formula. We first take the log likelihood, take the log likelihood, and take derivative over the over the theta. So I think this formula is somehow straightforward, because take the log, we have these two terms, and then this one is the integration, so we get the expectation here. The only thing here is we the the gradient. Yeah, and the gradient is plugged into each terms. So uh, So from this formula, we can see that we have this sampling because this is from the training data set. And this one is we need to sample from the P data, namely the model, current model from the model distribution. And we can see the target is that we want the model's distribution to match the uh, real data's distribution. To sample it, we need the Langevin dynamics. It have a sample from a P0 distribution and use a long steps to refine the example, refine the X. So it's very expensive for the high dimensional or and multi-model distribution because for each update we need update t t times. We need update the x t times, so it's very expensive, especially when the data is high dimensional, then the t will become larger. Uh, so energy-based model training is very slow. VAE is very fast. They can derive the elbow at this formula, and usually the first term is the reconstruction loss, and the second one is the re, re, regularization term. But the VAE has its own problems. Here, they talk about one problem. The VAE tend to assign high probability to regions with low density under the distribution. For example, from a paper, they found that when they train a VAE with the CIFAR-10 dataset, uh, they only train with CIFAR-10 dataset, but the region of the minutes data may also have high probability, or we say the probability of the X from the minutes is higher than probability from the CIFAR-10. Uh, even the model never see the data from minutes, so which is not is a problem for VE. But this won't happen in the energy-based model because the energy-based model use the uh, uh, yeah, it cannot happen in energy-based model. So in this paper, they just combine the VE and the energy-based models and the energy-based model. Uh, so we can see they define the VAEBM as the function h, phi and theta. Phi is the energy-based model parameter. Theta is the uh, decoder's parameter parameters. Uh, and the definition here we can see it's very similar to VE and energy-based model. This one, the p theta x, is just the VE's likelihood. And the z and the epsilon of energy phi is very close to the vanilla definition of energy-based model. The only difference is the denominator. Now the denominator have two sets of parameters. So from previous definition, we can easily derive that it's equal to these two terms. The first one is just the VAE loss with the encoder and the decoder. And the second one is the energy-based model loss over the energy-based model and also the decoder. This is energy-based models parameters. This is the decoder. So the authors found that it's not easy to optimize these models together. They have a lot of derivation in the appendix. uh, so they finally to find the main problem is on this gradient, especially this one. How can we compute the log p theta x? We they if they use another MCMC to sample for it for it is too expensive, so they want to disentangle these two models. Then they propose a two-stage training. First, they train the VAE model to maximize the first loss, and second stage, they fix the VAE model, including the decoder, and only train the energy-based model, only train the phi, only train the phi. So this one is we can write it in this way. We sample this first term is from the data set to sample from the data set and compute the energy. And second term, we sample from the current model from the model distribution and compute the energy and take gradient. So now we only need to consider how can we sample from the combination of the decoder and the energy-based model. Okay, they also explain a bit about why use two-stage job training. First, they avoid this uh, computing, this full definition. Second, because they first pre-train a VAE, so it has provided a good approximation to the real data distribution. Then the energy-based model will refine the distribution, so it will just need a small number of updates. So which means here the P0 is very close to the P, PD distribution. Then the MCMC can use won't take a long process to refine the refine the samples. They also have additional advantage is that the VE provide a latent space, uh, Z, Z and the epsilon. So it shows a lower dimensionality and a smooth distribution than the real data distribution, which also makes the MCMC more efficient. Okay, the final part, not final part, to optimize it, they have a further method, further improvement. They use the reparameterized sampling in the negative phrase, this part, because if they we know in VE we can use the reparameterization to sample from epsilon. Then the epsilon is the normal distribution, which is better than you directly sample from Z. So here they consider the same trick. The problem is that uh, they consider the joint space of epsilon Z and epsilon X, both from the normal distribution. Then we can see from this figure, they get the epsilon z to sample the z, and then pass the z with the epsilon x together to the decoder to get the x. So they sample x by in with this formula. So this one as the x0, we can see it's x0 to for the energy function, but uh, for the energy function and then apply the MC sampling. But I have a very small problem question about it because vanilla VAE only use this epsilon z to to sample z and get a final x. Uh, in in this paper, they define the epsilon z and epsilon x. So I'm not sure how how they how they get epsilon x to the decoder. I'm not yeah I'm not quite sure about it. Maybe it's from the NVAE paper because in this paper because they use the NVAE as the uh, backbone. Okay, the results. Uh, their results have a better FID score than previous VAE energy-based model method, and also the NVE with the NVE here, and also the NVE, and they can also see the MCMC sampling process, and they can apply the method on very high dimensional data like caliber A 25 6 20 times 25 6. Some here from the table 8, we can see even for different data sets, the long-run dynamic steps can be very small, like 10 is less than 10. So it's a very, it's much, it's a fast method because I think for the method like short run, short run energy-based model, it may use like 60 steps to train the energy-based model. So it's almost 10 times faster or six times faster. In table 4, they compare the different training methods, NVE itself and energy-based model itself, vanilla energy-based model. We can see the FID is not good. Then they consider use uh, use the NVE to sample the first to sample the x0 from the p0x. They use the NVE to replace it for the MC init initialization. So we can see it have a big improve. It already improved a lot to 2029. Finally, they use the NVE. They can uh, they sample from the hidden space. They sample from the hidden space Z. Then the FID can become better. So thank you.